Hey guys, welcome back to my 386 machine build video series. Last time you saw me emergency fix the mainboard because it mysteriously stopped working. I baked it, which revived it, but some of you said it was not a permanent thing. And what can I say, you were right. After about a week it stopped working again. I tried reflowing it once more, but it didn't fix anything. So yeah, I went hunting for a new mainboard. I was going for a 386 SX again because of the competition rules, but it turns out we interpreted the rules a bit stricter than they actually are, so I widened my search radius to include 386 DX machines and found this gem for a very reasonable price. Let's first take a tour of the mainboard before we start actually building the machine. So this one is a 386 DX clocked at 40 MHz. The difference between the SX I originally wanted to use and the DX is that the DX uses a 32-bit data bus. The new one is also socketed, which looks way cooler and means it's replaceable. The wider data bus means it can transfer twice as much data between memory and CPU per memory cycle. Of course, the rest of the system is still a 16-bit ISA-based design, so communication with peripherals will not be faster. The CPU on this one comes from AMD, but in the 386 days, those were perfect clones of Intel's original design, so it doesn't really matter if this is an Intel or AMD CPU. Though I think Intel never sold them clocked at 40 MHz, but AMD did. Because it's a 32-bit variant though, the memory sockets come in groups of 4 now, forming 2 banks. Each single inline module has an 8-bit interface, using 4 of them adds up to 32 bits. Another thing that will make this mainboard quite a bit faster is the presence of cache sockets. These add level 2 cache to the system, counteracting the comparatively slow DRAM. The mainboard has 128 kilobytes of cache installed, but can be upgraded to 256 kilobytes. The board comes with 7 16-bit ISA slots and 1 8-bit slot, though actually the 8-bit slot is electrically also a 16-bit one, just a mechanical slot is missing. Should I ever want 8 16-bit expansion cards, there's an option right there. This slot you see down here might look like another out-of-line ISA slot, but it's actually a slot to plug in memory expansion cards. As far as I know, those were vendor specific, and my chances of ever finding one for this board are close to 0. The last socket you see on this board is for the 387 floating point unit or numeric coprocessor. There isn't that much software that actually makes use of this for a 386, so it doesn't really matter if it's missing. I could have used it for the demo I'm working on, but then again, making it work without a numeric coprocessor means it can run on more computers. Now, this board is in pretty decent shape. I'll just have to bend those jumper headers straight again, and there is a tiny amount of oxidation going on where the battery once was. Nothing to desolder on this one. And another advantage is that with the help of my friend Sorceress, I found the jumper settings manual for that board, so no tedious reverse engineering here. Especially the cache jumpers look like they'd be hard work to figure out. Removing the battery damage was a lot easier this time than for the other mainboard. The hot glue residue was a bit more stubborn, and even after removing it a little stain remained, but that's okay. Finally I brushed off the little bit of dust that was there on the mainboard and used compressed air to remove it. Well, I guess let's give this thing a try then, shall we? Let's install some RAM. As mentioned earlier, we need to install 4 SIMs into one bank. Let's start with the first bank. These are 1 MB each, but I'm only going to install 4 of them for now, so we can see if the board works at all. Installing SIMs can be a bit fiddly. They have to be tilted just right so that they fit between the contacts. The old board had cheaper sockets, but those on this mainboard have proper metal clips to hold the memory, but they are also a bit more fiddly to work with. Just never use force. Once inserted, gently push them into the right position. Now, I've got the case for the machine here, so we can plug in the power supply. With AT power supplies like this, you must be careful not to swap the 2 plugs. Luckily, it's easy to get right. Just put the black wires together in the middle. You know this graphics card from the benchmarking video. Let's install it. This board is a lot sturdier than the old one, but I give it some extra support when installing the card anyway. I also want to install the PC speaker so I can hear if the BIOS generates any self-test error beeps. Its cable is too short though, so I just remove it from the case for a while. Power on, and this happened. Since this is a Mr. BIOS, I googled their error codes, and it turns out that this pattern, low, high and 4 times low, indicates a memory error in the first bank. I removed the SIMs again and realized that 2 of the pins were crushed. It's barely visible in this photo. I have installed hundreds of those over the years and I never damaged a single socket, so I don't think that was my fault, but it's possible. There's a first time for everything, I guess. Anyway, whoever is to blame, time to fix the problem. At first I tried to bend the pins back into their normal shape. I didn't expect much from this, and yeah, they just broke off. Luckily I have a broken 386 board now that I can strip for parts. First I wanted to replace the whole socket, but then I realized that the pins are not really held by the socket. Desoldering pins and pulling them out of the socket might be an option if the pins have the actual same shape. So I tried that, and guess what? They have exactly the same shape. So I pushed the new spare pins back into the socket and soldered them back in. So this put a lot less thermal stress on the board, and it looks much better with all sockets the same type. Sadly, I did the old camcorder trick where you stop the recording when you intend to start it and vice versa, so I have no footage of me soldering the pins back in. You'll just have to take my word for it. Now, did all that solve the problem? Nope. I double checked all the pins, measured their continuity and spent quite a while being baffled. And then I realized, this is not the first memory bank. Remember the picture from the beginning of the video? Well, let me tell you, it actually belongs like this. The old Mainboard's chipset was able to reorder memory banks internally, but this one always needs memory in bank 0. I guess I'm a bigger derp than I realized. So it probably worked all the time, the bent pins still making contact with the SIMs. But this way I found the problem with them, and the board will probably make fewer problems down the line. I installed memory in both banks and tried booting it again, and this time it just worked. It detected all the 8 MB of RAM, meaning the fixed socket actually works. Of course it complains about the battery being discharged. There is none. Since the mainboard doesn't have a CMOS battery anymore, we need an external battery. Otherwise the PC won't be able to store BIOS settings or keep the time correctly. You can get those ready-made and put them somewhere in the case using Velcro, or you can go the DIY way, which I chose to do. I have a generic 20mm coin cell holder here, a plug with the matching keying I stole from some other computer, a bit of perforated prototype board and a slot bracket from a broken graphics card. I first cut the PCB to size, marked off the position for the screw hole in the PCB and drilled that hole using my Dremel. Then I soldered the battery holder onto the board and attached the wires. All that's left now is screwing it onto the slot bracket and plopping in the CR2032 coin cell. That should do nicely. The mainboard has a header for external batteries like this. I first confirmed the polarity to see if the plug is the right way around, which was the case, and then I powered on the machine. The first thing we notice is that the message about the discharged battery has disappeared. Let's set the time and see if the machine keeps it updating while the power is off. And that seems to be the case, so we can assume it is working now. Back when 386s were made, mainboards didn't come with many peripheral connectors. As you can see, there are no floppy or hard disk connectors or even serial or parallel ports. Back then those were typically installed as an expansion card, and typically all of these things on one card. I got a few of those for free a while ago. This one is the cleanest and thus the most promising. Visually it looks okay, doesn't seem to have any leaking capacitors or shorted pins anywhere, but if it works it'll need some maintenance. But for now we just want to test it. I have a 3.5 inch high density floppy drive here. I've been using this one for quite a while and it has always been pretty reliable. When plugging in the floppy cable, make sure the red wire goes on the side that has pin 1 marked on the drive and on the controller card. Just add power and let's see what happens. The BIOS complains about a change in disk drive and communication port configurations, which probably means the controller is working. The BIOS setup now added the floppy drive tab. Interestingly, this BIOS supports 4 floppy drives, which is pretty rare. I've been asked to do a backup of the BIOS contents because of that. I'll do that later once the machine is done. For now, let's set drive 0 to the correct type and try to boot into DOS. I made a bootable disk with some benchmarks a while ago. Let's plop it in and see what happens. And yeah, I made this disk on a Windows 95 computer. The most interesting benchmark I'm interested in right now is speedsys. This one is often used in the retro community to compare machines, and this will be no exception. I'm doing all of this now before putting more of the machine together because I want to upgrade the cache next. But of course I want to know if the bigger cache even makes a difference, so it's nice to have a baseline. The memory test writes bigger and bigger blocks of memory to see how many bytes are transferred per second. You can see that the read and move speeds break down at the 128K block size mark, which indicates the cache of currently 128K is working. I'm saving a screenshot and a report of this for comparison later. Now that we know the performance with the small cache, let's replace it. The small chips on the left are the tag RAM, which basically store which part of main memory is stored where in the cache. The bigger ones are the actual cached main memory contents. I have 8 SRAM chips here. These are 32K by 8, which means they have 32,768 addressable data words, each holding 8 bits. Those are 15 nanosecond chips, which is actually quite a bit faster than needed for the 386. The mainboard has 25 nanosecond chips at the moment. They are fast enough for the cache controller to access them without stalling the CPU at all. So it would be possible to just add the 50 nanosecond chips to increase the size, but I would like to keep the same type of chip on the board. When installing new ones, be careful, the sockets allow you to put them in the wrong way, which may actually damage them. The sockets have a notch on one side and so have the chips, and that notch is usually also printed on the mainboard. I cannot replace the tag RAM because I don't have fitting chips, and the ones installed are actually exactly the right size for a 256K cache and are fast enough too. The last thing we need to do is configure the jumpers for the new cache size. According to the manual, this one needs to go here and that one here. The rest stays the way they are. Alright, time to boot the machine again and check speedsys. If the cache is working correctly, the breakdown of memory access speed should now be moved to the 256K block size mark. And that's exactly what we see. The new cache seems to be working. Great. Here's the result with the smaller cache again, and here it is with the bigger one. Another thing that caught my attention in the BIOS setup was that the memory is currently running at 1 wait state. That means the memory controller waits 1 additional clock cycle before assuming the memory has done its read or write operation. If we could set that to 0, uncached memory performance should increase too. It could make the system unstable though, if the RAM is actually too slow for that. But there's only one way to find out. So I set them to 0 wait states and ran speedsys again. Comparing the results, memory access got indeed a bit faster and the system seems to run stable. Nice! With the RAM, battery and cache stuff sorted out, we can now begin to assemble the machine. In one of the earlier videos I mentioned that the VGA card needs some maintenance. For one, the slot bracket is the wrong one and has the hole for the VGA jack in the wrong height. The VGA jack itself caused some trouble when plugging in the cable, so I'm going to replace that. And while I'm at it, I think it makes sense to replace the electrolytic caps. I've actually done all of that a while ago before the other mainboard died, but through the miracle of video editing it will look to you as if I've done this in this order. I began by removing the wrong slot bracket. Once that was done, I could desolder the VGA jack. It's always a bit tricky to get those huge blobs of solder removed, but in the end I managed to do it. Getting the new jack in was a lot easier. Then I replaced the capacitors one by one. With those electrolytic caps, it's important to get the polarity right, otherwise they will explode. The last thing to do was find a fitting slot bracket. I have a bunch of more or less old VGA cards, but it took me quite a while to find a bracket that has the correct dimensions. Once I found it, I attach it to the card, and now I have a VGA card that is as good as new. As I said, I did all of this before I even got the new mainboard, so no need to test the card, we've done that extensively already. The I/O controller card was pretty crusty too, and it also deserved a few new electrolytic capacitors. Also, the ISA edge connector was a bit rusty. The contacts are gold plated and don't rust themselves, but flash rust from other metal parts can still settle on them. So I took the card apart and first removed the old caps and soldered in new ones. Luckily there were only 3 of them, so that was a rather quick operation. Cleaning went fast, only removing the rust from the contacts took a bit of elbow grease and patience. I used vinegar and made sure to remove all the vinegar with alcohol. The vinegar salts might be conductive after all, and we don't want to cause any short circuits. Anyway, in the end the card looks almost like new. Usually I would have to check all the jumpers on it to see if the settings are correct, but sadly the only reference that I found online that appears to be for this card doesn't seem to be quite right. And since the card appears to work, I'll just keep it the way it is instead of trying to reverse engineer everything. The blue dot that someone painted onto the CPU has been bugging me all the time, but alcohol was indeed the solution here. Now that we have the basics done, it's time to start finally assembling everything. I begin by putting in the plastic spacers. I was looking for the right type that is inserted from the bottom for quite a while, but they are still being made, so I got a batch of them. With those it's easier to find the right holes to use by turning everything upside down and just putting the struts in. Sadly, the power switch sits pretty low in this case, so it's interfering with one of the spacers. I tried cutting the spacer down, this way it would only support the mainboard from the bottom without actually holding it in place. And I also put some tape on the bottom of the switch because parts of it are metal and I don't want to risk it getting into contact with some stuff on the mainboard. And the risk is real because right there are the jumpers for the cache configuration and the switch does actually push down on them, even making the board flex. And I've had some bad experience with flexing mainboards lately, so I looked for a way to avoid that. I tried removing the spacers on the switch itself, hoping that would move it close enough to the outside so that it would sit next to the board instead of on top of it. But there are another 5 or so millimeters missing. In the end, the solution was quite simple. I just put a thin piece of cardboard between the case and the switch on the lower side. This way the switch angles upwards ever so slightly that it just pushes the board enough to hold it in place. And on the outside, the case gives enough room for the switch's plastic cap to move freely even at that angle. With the mainboard finally installed and the power switch not breaking it, it's time for the relaxing part, where hopefully everything will just work. I began with all the cables that need to go onto the mainboard. It's easier to do that now than when all the other hardware is installed. I began with the power cables, black wires together in the middle, followed by the reset button and the turbo switch. The case comes with a double throw turbo switch, while the mainboard requires a simple single throw on-off switch. Luckily the plug is wired so that each of the 2 throws act like simple reversed on-off switches connecting the center to either of the 2 other pins. So simply figuring out which of the 2 pins will be connected in the switch's depressed state means I can connect those 2 on the mainboard. The speaker is no big mystery. Mainboards of this time often didn't have designated power LED connectors. Instead you could use the keyboard lock connector, which includes the power LED. I had to look up the pinup though, as I've never actually seen any of these before. Weirdly, those 2 pins down here are called turbo LED in the mainboard's manual, but there's a jumper installed right now. I took the jumper off and confirmed with my multimeter that it is indeed the turbo LED. I don't know why anyone would put a jumper there, and luckily shorting it didn't draw enough power to damage anything it seems. But that meant I could also install this LED now. With that done, I could install the new CMOS battery we made earlier, followed by the I/O card and the graphics card. The hard disk activity LED needs to be plugged into the I/O card. Of course, I need some sort of hard disk storage in this machine. Actual hard disks from the time are hard to come by, and when you find one, you never know how long they will survive. So I opted for an SD card adapter instead. SD cards should be around for a couple more years, they are cheap and their storage space is hilariously huge for a 386. But the question is how to fit this small adapter into the case, which has only 5¼ and 3½ inch drive bays. The answer is this 2½ to 3½ inch mounting frame. The drill holes don't fit perfectly, but close enough for this to work. This would be enough to mount the adapter in a drive cage in the case. But you see, I don't have any fitting drive bay covers for this case. And I have to fill 4 external drive bays with something. And I just happen to have this lying around. That's an old hard drive caddy that allows easy access to the hard drive without even opening the case. I decided to put the adapter in there so I can access the SD card easily. There are other card adapters that you put into an extension card slot, but I think this solution is much cooler. There is one problem with this caddy though. I don't have the key for the lock anymore, and without it being locked, the electronics won't allow access to the drive. But there's an easy solution to that. I'll simply mod the PCB by shorting the 2 wires going to the lock. This way the electronics always think the lock is closed and will grant access to the drive. With that done, I can install the frame into the case and plug in the cables. With the floppy drive, I decided to at least do some preventive maintenance. After opening it up, I cleaned the read-write heads with alcohol and removed some dust that had accumulated. Then I added some fresh silicone grease to the spindle and rails for the head actuator. Installing the drive is a bit more tedious because the screws on the right side can only be reached while the cage is not mounted into the case. But afterwards I realized my method was not necessarily the most efficient, but whatever. All that matters is that now I have a fully working 386 PC. Time to test what we've got so far. I pulled out the smallest SD card that I could find, which is still 1 GB. I put it into the adapter into the machine, and configured the BIOS for the card. The way you typically do that is set it to use 16 heads and 63 sectors, and whatever number of cylinders you need to get the size of your card, or just 1023 for maximum compatibility. I'll start with that. Interestingly, when I tried to boot the machine with this card installed, this is what happens. I had no idea what the reason was until I tried a different SD card. This one is a 16 GB SDHC and, well, it works just fine. Maybe the adapter doesn't like the old SD card, no idea. If you have any idea why the older card doesn't work, please let me know. So for testing, I booted from a DOS setup disk, partitioned the SD card and formatted it using the S flag to copy system files over, which basically makes this a very minimal DOS drive. The formatting is not sped up, by the way. If you ever formatted a bigger hard drive back then, you know how long it could take, so this SD card is really something. But now we know the floppy drive and hard disk work, so let's install a full DOS. I'm going with DOS 5 here. I'm running DOS 6.22 on my 486, so I feel like it's appropriate to go a bit lower here. It's also literally the first operating system that I used on my own computer, so it's actually pretty nostalgic for me. I don't have an English keyboard, so let me pick German here quickly. And as much as I liked DOS shell as a kid, I really don't need it to run every time I boot the computer. Let's do a normal install to CDOS and let it pick all the disk space, which means it will reformat. I'm speeding up the installation process here a bit because it takes a few minutes to load stuff from the floppy disks. Those are only 720K disks, while DOS 6 already came on 3 high density or 1.44 MB disks. And done. Look how fast this thing boots, that's amazing. Now that we've got ourselves a fully working computer, let's talk extras. There are 2 drive bays left and it would be a shame to let them go to waste, especially since I don't have any fitting covers for those. Remember the beginning of the video where I mentioned the BIOS supports 4 floppy drives? Let's put 2 more drives in there, shall we? For the remaining 3.5-inch drive bay, I picked a floppy drive emulator. This one is from Gotek and I've used the same model for my Amiga build. It'll need a proper firmware, but is new otherwise. And the big 5.25-inch drive bay will get a nice old floppy drive. This is a generic 1.2 MB drive and it's in perfect working condition and clean, so no extra work required here. I'm starting with the Gotek drive. I've done this whole procedure before in my Amiga video, so this will be a short version of it only. The firmware on this thing contains a bootloader that allows programming through a serial port. To access it, we need to be able to add a jumper that makes the bootloader enter programming mode. And we need some more pins to connect the receive and transmit wires of the serial connection. Then we attach a serial port and 5 volts power. I've built this little adapter for the Amiga video as well, finally a chance to reuse it. This time I'm going with the Flash Floppy open source firmware. Let's see how that works. And that's it. I just need to put it all back together. To install the Gotek and the 5¼ inch drives, I have to remove the 3½ inch drive bay again, but then it's just tightening the screws again. Now for the part that gave me headaches for a while. The BIOS supports 2 floppy controllers, each driving 2 drives. I had 1 controller card installed already, as you saw earlier. But I have 2 more cards. This one features 2 serial ports, one of which is available without an additional cable and jack, as well as a parallel port, an IDE interface, a floppy controller and another internal game port. On this card, just as on the one that is already installed, the floppy controller can be configured to be either primary or secondary. The other one I've got looks pretty similar and they use the same chip actually, but they are configured quite differently. This one also has the external parallel port, but instead of the serial port, the game port is made available on the slot bracket. The serial ports are only available internally, and for some annoying reason the floppy controller cannot be configured to be the secondary. Naturally, I tried to make the 3 floppy setup work with the card I had already installed. So I used the additional card that can be configured for secondary floppy controller and plugged it in. I wired the actual 3½ inch drive to be drive 1 on the primary, the Gotek to be drive 1 on the secondary, and the 5¼ inch drive to be drive 2 on the secondary. When booting, the BIOS immediately recognized the new floppy controller, and when entering the floppy setup menu now, it allows picking on which controller each of the configured floppy drives are installed. You can see that here with the little P and S indicating that it is either primary or secondary. It all looked fine and dandy, but after booting it turned out that whichever floppy drive is attached to the primary controller doesn't work quite right. I can select the drive and when trying to access it, it actually starts working, but whatever I do, it only returns empty disk contents. The other 2 drives connected to the secondary controller work fine though. So I tried swapping the primary and secondary controller around, but the effect was the same. Whichever drive is attached to the card I had installed earlier didn't work. Okay, I really wanted to use that card, so I picked the other one of the 2 new cards. The old card was configured as secondary already anyway. But same effect. But out of curiosity I tried the 2 new cards and, well, they worked just fine. So I guess the 1 card is to blame. That means all the cleaning and maintenance were for nothing, but I can still use this card in some other project. But it also meant I had to refurbish these cards as well. They were seriously dirty and one of them only worked at all after cleaning the contacts. I'll just give you a time lapse of this, you've seen me do that a few times now already. Now let's set the jumpers on these cards. I removed all of them so I can set them exactly to what I want. I decided to enable the parallel ports on both of them. I don't think I'll ever use them, but I don't like the idea of having external connectors that don't work. This card will be the primary floppy controller, the IDE controller, and the secondary parallel port. Let's set the jumpers. Parallel port is secondary, serial port 1 is off, floppy controller is on, IDE controller is on. We don't care about these 2 because we don't use serial ports. This one to disable serial port 2 as well. Enable parallel port and disable the game port. This one has an external game port, but I want to use the one on the Sound Blaster I'm going to install soon. And then we have to set the interrupt request lines for the serial ports, which we don't care about, so I leave them out, and for the parallel port. The first 2 parallel ports on the PC share IRQ7, so I'm picking that. This card will be the secondary floppy controller, serial port 1 and 2, and the primary parallel port. The floppy controller is enabled, and it is set to secondary. The IDE interface is disabled. I don't think I'll ever put more hard disk or a CD-ROM in here. That also means we can ignore the next 3 jumpers. Serial port 1 is enabled and it is set to COM1, and serial port 2 is enabled and set to COM2. And finally, the parallel port is enabled and set to LPT1. Finally, I began putting labels onto the 2 cards because I already began confusing them. Then I had to remove the old I/O card and the graphics card because I'll do some reorganization. There's also the thing that we enabled the internal serial port on one of the cards and need to put a jack somewhere to make use of it. I could open up one of the holes on the case, but remember the battery holder? I made it from an old VGA card slot bracket and it had a sub-D jack shaped hole in it anyway. So putting a jack in here made good use of that. Reinstalling the cards, I began with the VGA card, then the primary floppy and IDE controller card. It'll be hard to reach the connectors later, so I'm plugging them in right now. Getting the second card in with all the cables was still easier than trying to get the cables plugged in with the second card already installed. Before adding the final components, a network adapter and a sound card, let's tidy up a bit. I don't like all those cables getting into the way, and I've actually had cases where the 12-volt pin of one of the big Molex connectors touched a screw or something, caused a short circuit and damaged the power supply. So I'm strapping them all down. This is the sound card we're going to use. It's a Sound Blaster 16, model number CT2230. I would have loved to use an 8-bit Sound Blaster Pro or a Gravis Ultrasound instead, but those are hard to get and very expensive. The Sound Blaster is pretty dirty, mostly yellowish and very sticky dust. So the first step, as always, is cleaning the damn thing. The audio jacks seem to have a lot of dirt in them too. To clean them, I removed some of the cotton of a Q-tip, soaked the remaining bit with alcohol and scrubbed. That seemed to work quite well. The slot bracket looked somewhat disgusting, but after rinsing it with water and soap, it looks almost like new. Of course, I want to replace the capacitors on this card as well. Here it might actually make a small difference in terms of sound instead of just preventing a possible future failure. This card also has a ton of capacitors, a total of 44, using 6 different capacities. I marked them all off and made a printout so that I can tick off which ones I have replaced already. Sadly, I didn't have any 1 microfarad caps left, so I'll replace the other ones, then make sure the card works and install the drivers and all, then go back to replacing the remaining 14 caps once I have them. This was the biggest recapping job I've done so far, and in an evil touch of the designers, some of the polarities are marked incorrectly on the silk screen. So when you attempt this maintenance, make sure you use the installed caps as reference, not necessarily the silk screen. But after a while it was done and I could reassemble the card. Quick check of the jumper settings. The base address is 220 hex, which is the most common for Sound Blasters. This is a software configured card, so we don't need to set in jumpers for the low and high DMA channels or the interrupt request line. I want the MPU MIDI interface emulation enabled, and I want it at a typical address of 330 hex. The card has a socket for Creative Labs Advanced Signal Processor, but I don't have or want the chip, so we will disable that function. I want the joystick interface to be enabled, and lastly I'll keep the CD interface enabled, though I don't think I'll use it. Those jumpers were all set like that already, so nothing to do for me except actually putting the card into the computer. I wanted to install the Sound Blaster in the last ISA slot, but it doesn't fit. The memory modules are in the way. And we are really lucky that there's a gap between the memory modules that lines up with the second remaining slot, otherwise it would have been tricky to get the Sound Blaster installed. But here it fits between the memory modules. I don't have the original driver disk, so I downloaded an archive of it and created the disk image. Using Linux, that's pretty easy. I just create a file of the appropriate size, format it as FAT12, mount it, and extract the driver disk contents to it. Using the GoTech drive, this is really the easiest way to transfer a few files to the machine for now. As a first test, we can just launch diagnose.exe from the disk. It asks for the I/O address that we had configured the card to, and then for the DMI channels and interrupt request lines we want the card to use. With that done, we can test the card for the first time. And it seems to work fine. That's quite a relief after all that soldering.
16-bit testing.
Now, we could just use the installer program, but it installs a lot of stuff we don't actually need. All we want to do is run this resource configuration at boot. And the tool to do that is diagnose.exe. So let's make a directory for it on the hard disk and copy it over. Let's edit AutoExecBut to include the Sound Blaster stuff. Diagnose.exe has two functions. It can look for plug-and-play cards and set the blaster variable for us, or it can use a preset blaster variable to set up software configurable cards like mine. What we need to do is set the blaster environment variable to contain the resources we picked earlier. The blaster variable has a few fields we need to set. First, the I/O port base address we jumped out earlier, which is 220. Then the interrupt request line we want to use, 5 is pretty standard and it should be free. Then the low DMA channel. We used one before and no other hardware seemed to use it, so let's keep it. Next we have the base address of the MIDI port, which we jumpered to 330. And finally, since this is a 16-bit Sound Blaster, we need to pick the high DMA channel. We used 5 before, so let's keep it. Finally, we need to call diagnose.exe with the /s flag, which means it won't run the user interface, but instead configure the card. Let's reboot and see if it works. That doesn't sound too bad. I only recorded that through my camera's cheap microphone, but all in all I'm pleased with the result. In the meantime, I also got the remaining capacitors, so I took out the card and replaced those as well. And that's the Sound Blaster done. All that is left now is networking and finishing everything up. That's the network adapter we're going to use. It's an Intel EtherExpress Pro 10 Plus and it is in pretty good shape, and apparently it is okay. The slot bracket is a bit dirty and I want to get rid of that marker writing. But other than that, there's not much to do except install it. There's a single usable 16-bit ISA slot left, so in it goes. Of course, nowadays I want TCP networking and none of that novel stuff. So what we need for that is a packet driver for the card and a set of tools for using TCP. The packet driver for this card is a single program called epropkt.com, and I'm just copying to the hard disk and add it to AutoExecBut. I need to call the program and pass a single parameter, which is the software interrupt used to communicate with the driver. 60 hex seems to be a standard choice, so I'm going with that. After a quick reboot, the driver is loaded and it successfully detects the card. There's a great set of TCP applications for DOS called mTCP. These come with all the basic stuff you need, a DHCP client, HTTP and FTP server and client, and even an IRC client. Again, I copied the stuff over using a floppy image and the GoTech. We also need to create a configuration file for MTCP, but there's a sample configuration we can just copy and keep as is. All we need to do is set another environment variable called mtcp-cfg that points to the configuration file we just created. I'm also adding mtcp's directory to the path, so I can call it directly. A quick reboot and we should be able to use the network card. For now I'm just calling the DHCP client manually and it very successfully obtains the network configuration from my DHCP server. Let's try to ping something on the internet. That works just fine. And I also said hi to the people on the best IRC channel on the internet. I'm going to clean up my boot process later, I don't think I need to bother you guys with that. So yeah, networking seems to work just fine. On to the last segment, almost done. And there's not much to finish up. I just need to put in the last 2 slot brackets. Then close the case. And a finishing touch, a sticker marking this as the DGC 386. And I guess that's it for this video series. What a marathon! It took way longer than I had anticipated with the mainboard breaking and the time I needed to get a new one, but I think the result is worth the effort. I'm really pleased with how this machine turned out. It'll need some manual tuning of BIOS parameters and such and a more convenient boot setup, but I'm going to have a lot of fun with this. You may have heard it too, while making this video I was hit by 2 different colds. I hope it didn't sound too scary. But if you liked the video, please leave a comment, subscribe, give it a thumbs up and share it. Sharing is caring after all, isn't it? See you all next time, bye!